Hello, come along in. All right, so today I'm going to talk about the Higgs boson, also known as God particle, and I'll explain why or why not it should be called the God particle. This is a beautiful picture done, drawing piece of art done by my collaborator Shanti Chandrasekhar. She's an Indian artist, she lives nearby here, and we've had 5 common science and art exhibitions so far, and we have another one coming up in about a week at the National Academy of Science. Her beautiful art, you can see that, it's all done by hand. That's called Scalar Fields, Emergence of Particles. Her art is inspired by science, by space, time, Big Bang, black holes, and so on. And I write pieces of writing, science writing, that goes with her art. And this one, she called it Scalar Field. Now, the Higgs boson is a scalar field. A scalar and vector. You may know vector is something with a direction. A vector field, like electricity and magnetism, have directions. A scalar field has no direction. It's just a value everywhere. And I'll explain a bit about that. We actually had I just brought a book to show you. We had a catalogue of the first exhibition we did at the American University Katzen Gallery. It's out of print now, unfortunately. We're trying to get more printing made, but we might one day. But that's got her art and my writing in there. So that's that, and I'm going to, so with this art, I bought that piece actually, I own it. Wow, it's so beautiful. I couldn't resist buying it. Eh? It's colored pen on paper. She's a brilliant artist. Now, this is a piece of writing that goes with that piece, so I'll actually read it out because it is a sort of summary, a short piece of writing that goes with scalar fields. And this is a summary of the talk. Electric and magnetic fields are everywhere, varying in strength and direction. In 1964, some theoretical physicists had the idea that there's another field that has no direction, just a value, which is the same throughout the universe. Peter Higgs said that if that field exists, it should have a particle going with it, like the photon is the particle of the electromagnetic field. Unlike the photon, this particle would have a mass and decay very rapidly to lighter particles. It explains how free neutrons decay to protons, allowing hydrogen and you to exist. After decades of searching, it was discovered in 2012 at the Large Hadron Collider at CERN in Geneva by me and thousands of other physicists. So, about science and art. Science and art go so well together. And this is it's a bubble chamber picture. So what you see here, you may have seen these things before. So when a charged particle goes through a liquid that's almost boiling but not quite boiling, and then you expand the liquid, and along the tracks of the particles, it's kicked out electrons of the atoms along the track, making a trail of ions. And when you just expand it just about boiling point, the bubbles form along the tracks of the ionization. And then you take pictures of those. We did thousands of these pictures. That's in a big tank of liquid hydrogen that's just about boiling. And then a beam of particles is sent through, and it leaves these tracks. And what you can see is, for example, the tracks are curved because it's in a magnetic field, and charged particles with positive bend one way, negative bend the other way. And as they lose energy going through the liquid and ionizing the liquid atoms, they spiral around and lose energy and spiral down. And you can see lots of structures in here. I put that up as a piece of art, but also to explain how we can see particles, even though they're much too small. We can see the tracks they make. Like a bit, if you see a white line in the blue sky and it's going across the sky, you can't see the plane, but you know it's there because it's leaving a trail. So that's how we can see things much more than we can see directly with our eyes. Like a shooting star as well. You may have seen a shooting star. It's really a meteorite, like a grain of sand, maybe 50 kilometers high, but you see it by the trail it makes. So this is how we can see particles. So now about fields, you know electricity and magnetism, of course. I have this very nice little magnetic thing. You may have seen these little bar magnets with things, and you can make all sorts of constructions out of them. It's a lot of fun to these things. Get one for your grandkids or kids and play with that. So those magnets, you've all played with them. They have a direction. The force has a direction, like electric force. So you know, you've probably seen on a dry day, you can comb your hair and you can pull your hair up with electrostatic force. So electricity and magnetism have directions, and they vary from place to place. Gravity also has a direction. You drop this, you fall to the ground. So those are forces with direction, and they vary from place to place. The Higgs field is a field that doesn't have any direction. And the particles that go with the Higgs field, like the photons are particles of light, and they're Higgs bosons. So going back about unification of forces, back in the 19th century, Michael Faraday, English, James Clerk Maxwell, Scottish. And Maxwell actually you can make measurements of electricity and magnetism in the lab, and he developed equations for the electric and magnetic forces, and realized that out of those constants you measure in the lab, a speed came. And out of the equations it came at 186,000 miles a second, or about 300,000 kilometers a second, and that's the speed of light. So he got the speed of light from measuring electricity and magnetism in his lab, and putting them together in a set of equations, unifying electricity and magnetism. So that's why we call it now electromagnetism, as one force. And you can't read the equation on a T-shirt, but it's got Maxwell's equations, and God said delta B D equals 0, and so on. These equations. So that was, and radio, microwaves, heat, light, X-rays, gamma rays, they're all electromagnetic waves of different frequencies or periods. Light is just a small part of the spectrum that we see with our eyes, but radio waves are long wavelength light, if you like. Now this is a busy-ish slide. I don't expect you to go through the whole thing, but this is a chart of the fundamental particles that we have found and know about. And on the left is called fermions, named after Enrico Fermi. Enrico Fermi was an Italian physicist who went to Stockholm to get a Nobel Prize in 1939 with his Jewish wife, and they didn't go back to Italy. They came to America afterwards, and Fermi came to America, and he started the first nuclear reactor in a squash court in Chicago. He managed to get a nuclear pile. He got a few tens of watts out of it before they damped it down, but that was a demonstration that you get nuclear energy out of atoms. As Einstein had said, energy and mass are the same thing. And the other particles are called bosons, named after Satyendranath Bose, an Indian mathematician and theoretical physicist who was a Unitarian, by the way, so I put that there. And Bose, his brilliant idea was that photons, let me go back. Electrons, you can't have two electrons in exactly the same place and the same time. So when you have a hydrogen atom, well, let's say a helium atom has two electrons in the inner shell, one is spin up, one spin down, so they are different. And you can't put more in because electrons don't, or other fermions too, they can't stand having somebody else in the same couch bed, if you like, but whatever. Whereas bosons, and Bose said photons, which are particles of light, according to Einstein, they can pile on top of each other. You can have many on the same, they like to be together. It's a bit, an analogy is like we had these trains with compartments. A train comes into the station, and if you can only get two people in a compartment, they're fermions, but if more and more people like to pile into the same compartment, they're bosons. And a laser works because the photons coming out of the laser all like to be in the same state. It's called a Bose condensate. And he explains also superconductivity, where you have the electrons flowing they're in pairs, but that's another story. Anyway, what I put a red ellipse around U, D, and E, because those three fundamental particles are what makes up us. All are elements in our body which are made of atoms with a nucleus made of protons and neutrons stuck together, an electron going around in waves, waving around that. So now the protons and neutrons are made out of smaller particles called quarks, U for up and D for down. And the proton has got two up quarks and one down quark. The neutron has got, I shouldn't have hit that, okay. There we go. Right. And the neutrons, 2 downs and 1 up. That's the only difference between them. Now, here's another miracle of physics. I've talked about that here. Why is a neutron unstable? It decays on average in 15 minutes, but the proton is stable and lives essentially forever, at least more than 10 to the 30 years. The difference is only because the neutron has 1 down quark, the proton has 1 up quark. And the down quark is a little bit heavier than the up quark, allowing it to decay. And the reason is mysterious. It seems to be random, but that little change makes us possible and stable matter and so on. Anyway, the difference between fermions named after Fermi and bosons named after Bose are in the spin, or intrinsic angular momentum particles. The quarks and leptons on the left spin 1/2, and they are particles that cannot be 2 in exactly the same state. On the right, you have the bosons, and the Z and W are the exchange particles of a weak interaction. The photon is called a gamma. That's a gamma symbol up there. That's for photons. And G stands for gluon, which is the force particle holding quarks together. That's a bit technical. You can forget about that if you like. But I want to say about quarks. They make up protons and neutrons, but they're much, much, much smaller. You see here a proton. Well, if a proton is the size of this room, then the quarks are about the size of pinheads in the middle of the room, or grains of sand in the middle of the room. So if that's a diagram, proton there, and you zoom in on, magnify that little circle in the middle to this size, and quarks are still smaller than that. At most 1/5000th the size of protons, and proton is to atom as pinhead is to house. So they're so small. How can we see them? Well, we can't see them directly, but we can see them because they make particles that make these tracks like in the bubble chamber that I showed you before. So here's an example of a collision of 2 protons at the Large Hadron Collider. And it's in the early days when we only had 1 interaction happening at the time. The 2 protons, they go in a circular ring, which I will show you a picture of, that's 27 kilometers around, and they collide at various places around the ring. And in this event, they've collided, and 2 jets or sprays of particles have come out sideways. Those have been kicked out of the inside of the proton by 2 quarks, or actually gluons in this case, gluons, that are so much smaller than the proton, but they've got close enough to scatter out sideways and turn into jets of particles or sprays of particles, which are detected in the cylinder around there. And the red blobs are energy dumped by those so-called jets. And by measuring these scatterings, we have determined the size of these quarks and gluons. At least they're smaller than 1/5000th the size of the proton. Now, okay, the Z bosons that I mentioned before as quanta of the weak interaction, they can be radiated off proton. On the left diagram, the black or blue lines are protons that emit a virtual Z boson, which can scatter to produce 2 real ones by exchanging a Z. You see these triple vertices, Z, Z, Z vertex. Now, that is a diagram, a so-called Feynman diagram, that you can use to calculate the probability of these processes happening. And with just the Z boson exchange there in the vertical line between the 2 scattering Zs, you can calculate that diagram, and the probability would grow with energy, like the square of the energy. And if you keep going, it would go up and become bigger than 1. And you can't have a probability of anything bigger than 1, right? It's ridiculous. So something has to happen to stop the probability of that process getting bigger than 1. It's called a unitarity violation. So the theory is that there's something else that can be exchanged there called a Higgs boson, called H there. And that goes in that vertical line there, if it exists, and cancels out the Z and stops it exceeding a probability exceeding 1. There's another diagram on the right here, which you can see is turning around, and 2 Z bosons can fuse together to make a Higgs boson, which then decays to 2 Zs. Now, the Higgs is actually lighter than 2 Zs, so you have to borrow energy for 1. But anyway, this H is a quantum of this Higgs field. I'll say a bit more about it. And it's a particle that has no electric charge, it's got no spin, it's just got mass. And when it's created in a proton collision, it travels many diameters of protons before it decays away. So now a bit of Bible study. In the beginning was the Word. And this is a timeline from the very top, the beginning of the Big Bang and the end of the Big Bang. And at the top beginning, it seemed with only one force, unified force. And then at the end of the Big Bang, when the universe was about the size of a baseball, something happened. Space stopped expanding exponentially fast and started expanding more slowly. And the forces separated out into a weak force, electromagnetic force, and strong force. Those at the very beginning of before the Big Bang were one single force, according to theory. And then what's called a symmetry breaking occurred. The forces separated out. The weak bosons got their mass, and the photons stayed massless. So in the beginning was one unified force. That's totally symmetric sort of universe. But as it expanded and cooled, the symmetry was broken. That was the Big Bang, and the forces became different. Particles got their mass. Now, so on the right, I've shown this, put their star there. Before that time, which was, in the very first seconds of the universe, actually, the Higgs field was 0, and then it became non-zero by something called, well, it's a symmetry breaking. It's like a symmetry. If you have a pencil balanced on its point, a perfectly symmetric pencil, you balance it on its point, you know it's not going to stay there for very long. Okay. Of course, it's going to get kicked around by molecules in the atmosphere, but even without that, it's an unstable point, and it's going to fall in one direction or the other. It can fall in any direction. And that's represented by this Mexican hat potential, where that ball at the top of the thing is representing a vacuum with perfect symmetry, but then it rolls down in one direction or the other. It could roll down in any direction, and that's called a symmetry breaking. The symmetry of looking down at the top of the pencil, perfectly symmetric, is broken by it falling one way or the other. So that's called spontaneous symmetry breaking, and it's reason how particles like the fermions and bosons I talked about get their mass. Before that, they had no mass. So this idea that there's a field filling the universe, so you can, okay, I have electrons in my atoms in my little finger, and there's atoms in Andromeda Galaxy, and they've got the same mass. And you can create an electron out of a photon. How does it know what mass to have? Anywhere in the universe, the same mass. So these theorists at the top decided that there was perhaps this field through the universe, perfectly uniform, no special direction, just a value. And it's a field responsible for this symmetry breaking between the weak force and the electromagnetic force. Now Higgs, he was the one who said, if this field exists, there should be a particle that goes with it, a quantum of that field. Actually, he sent a paper along with the other people, and the paper was rejected by the journal, and then while he was revising it to resubmit it, he had the idea, maybe there's a quantum going with it, and a boson, and that's why it's called the Higgs field, because he predicted the particle, and that's a picture of Peter Higgs. He died only 2 years ago now, actually, with some equation on the blackboard there about complicated. In fact, this is a Sidney Harris cartoon, but this is the simplified version for the general public. Sidney Harris, great cartoons, okay. So I'm trying to be simple. So how to simplify this without going into equations? So Margaret Thatcher, who was Prime Minister at the time, and she was interested in CERN, she had a chemistry degree, so she was a scientific background. And she set a competition, said, I want you to try and explain this Higgs field or the Higgs boson to me in simple terms. And they had a competition, and the winner of the competition was, I forget the name, somebody I knew, but here's the analogy. She was called the Iron Lady in those days, she was a very tough woman. And you imagine a cocktail party of conservative people there, and Margaret Thatcher comes into the cocktail party, and she could walk straight across, but she gets crowded around by people wanting to talk with her, and they crowd around her and make it harder for her to pass through the room, you see. So this is an exact analogy of how particles are slowed down in their passage. If they didn't have this Higgs field around them, they would go at the speed of light. And actually, at some time when I was at CERN, there was a question some of the British wanted. They said, why are we spending all this money overseas? We could use that money ourselves for our physics project at home. And there was a threat that Britain was going to pull out of CERN. And actually, she put her foot down in the end and said, no, we're staying in, which was the end of a sort of difficult time for us. Now, this is a better analogy, if you like. If that Higgs field wasn't there, particles would not have mass. They would lose their mass. They'd go at the speed of light. All the particles would travel at the speed of light if the Higgs field wasn't there. Now, here's this is a bit tricky diagram, but it's just a space-time diagram with space going vertically, time going horizontally, and the speed of light is at 45 degrees because it's 1 second of time equals 186,000 miles of space, or 300,000 kilometers of space. That's the speed of light, 300,000 kilometers per second. So you draw the speed of light as a line at 45 degrees. And a photon or particle of light goes along that diagonal line. And so would an electron or a quark if it had no mass. So I tried to sketch this here. Actually, on the left you see that red line. It's showing that an electron, that's an electron, say, it's going at the speed of light, and then it gets kicked back by this field to go at the speed of light in the other direction. And then it goes kicked forward and kicked back and kicked forward. And because it keeps getting kicked backwards and forwards, it goes slower than light speed. So it's picked up some mass. Now, the scale is actually trillion times smaller. This happens at a scale of about 10 to the minus 40 seconds or whatever. So how does that translate to a particle at rest? I've shown a particle. It doesn't go at the speed of light because it's being kicked backwards and forwards by this Higgs field. It's going along at the speed of light, kick back forward, every time it hits this Higgs field, and that interacts with it and kicks it backwards in. Now, if you want to see how is a particle at rest, well, we know a particle can never really be at rest by Heisenberg's uncertainty principle, but if I've drawn on the right, particle at rest, and it's going off at the speed of light in any random direction, but it hits this Higgs field and it kicks it back. It goes off in another direction and kicks back. It's never at rest. It's jiggling forward, backwards, in all different directions. So it actually gets kicked back all the time. And so it's actually become sort of a fuzzy particle, not a perfect point. If it has more mass, it gets kicked back more strongly. So the top quark, which is the heaviest of the quarks, actually gets kicked back more strongly by the field, and so it's effectively smaller than an electron. So that's a sort of picture. If you can get along with that picture, that's an analogy. Analogies are never perfect, of course. Theorists might say, well, it's not exactly like that, but I think it's like that. So there you are. Now, this is, I just put this in because back in '88, I saw this paper about the Higgs boson by Kahn and so on. And there's diagrams on the left are these diagrams about how the Higgs boson can actually be produced and decay to 2 gamma rays. On the right, that's the figure from his paper, and it's showing the probability of a Higgs boson which mass wasn't known. On the left of the plot, you see 1 GeV. It could have been as light as 1 GeV. On the right, you see 100 GeV mass for this particle. And there's a line going up top right called gamma, which is photons, and that's the Higgs decay to 2 gamma rays, like you see in the bottom left diagram, and it rises strongly with mass. And the blue arrow there is where the Higgs actually was found at 125 GeV, and there you see that the decay to 2 gamma rays is only 1 in 1,000, 0.1% is the probability of decaying to 2 gamma rays. But if the mass of the Higgs is less than 180 GeV, decays to gamma gamma would be possible, also to 2 Z bosons, and that would give a narrow peak, but very small peak on the distribution, and I will show you that later. He said in his paper, the intermediate mass Higgs is a very challenging problem for future hadron colliders. But I picked up on that, and I thought, if we could measure those gamma rays extremely precisely, with very little spread in their energy that we measure, we might see it in gamma gamma decays. So I put together a paper in 1989 with my friend Jim Verdi, who's now a fellow of the Royal Society. I was at Stockholm University then, seeking an intermediate mass Higgs boson. And so the most practical search strategy seems to be to construct a high luminosity proton-proton collider, energy range within a factor of 2 of 4 TeV, and to make specialized searches in gamma-gamma channel and ZZ channel to go into electrons and muons. Dedicated experiments which can handle a high luminosity and still give a signal to background ratio, allowing the discovery of a standard model Higgs in this mass region, although difficult, do not look impossible. That's a little diagram just showing, as a function of the mass, which we didn't know, the so-called width of the peak that we would see in the distribution. And that's actually sort of how it was discovered 23 years later, which I'll come back to. But unfortunately, I didn't publish that paper. If I could send a message back to myself in 89, say, drop everything, publish that, you see, but I didn't. I organized a workshop in Stockholm about making photon detectors with super high resolution using liquid xenon and so on. And Jim Verdi came and he gave a talk about this. And he actually was leader of the experiment that found it later. But I left Stockholm and came over to Fermilab. And then in 2001, I had another idea about how we might find the Higgs. The two protons colliding, and they fly through each other. And you could pick a gluon, actually 2 gluons out of each proton, and they could combine and form a Higgs boson. And we published a letter of intent to Fermilab, a search for the Higgs boson using very forward tracking detectors to detect the protons as they went out. Now, this would require putting proton detectors in the Tevatron first, and it wasn't going to work there. The Higgs was too heavy, too low probability of being produced, but it could work at the LHC if you put proton detectors 420 meters away from the collision point, way down the beamline. And that hasn't happened yet. We were thinking this may be the way to discover the Higgs boson, but shortly after we'd proposed that, it was discovered by the gamma-gamma mode, so this was put on the side. It could still happen, maybe in 2035, so it's still a future project. But before that, this is me in the tunnel of the Tevatron, putting apparatus down in the beam to detect these forward protons that come out going down the beamline. And we did good physics with that. But we would have needed to do that one in each outstream direction. And we finally have done that where we put forward detectors in the Large Hadron Collider. But that's one of the things I was working on at Tevatron. That was in 2001. So now to the Large Hadron Collider. So this is a picture of the footprint of the Large Hadron Collider at Geneva, at CERN in Geneva. It's crossing the Swiss-French border. You see the Alps in the background with Mont Blanc there, the highest peak in the Alps, highest peak in Europe. And down below you see the Lake Léman or Lake Geneva, and the Geneva town is down there. You can see a horizontal line which is the airport, the runway. And the Large Hadron Collider is an underground tunnel, 16 miles around, or 27 kilometers underground all the way around. And all around there's magnets to bend the paths of protons going in both directions, opposite directions. And there are 3 places where those beams are focused down to the size of a hair and collide. One is CMS, where I put on the left there. It's a whole drive away from the center of where CERN is. So that's the Large Hadron Collider. And here you see a picture inside the Large Hadron Collider, that tunnel. It's 27 kilometers of superconducting magnets at 2 degrees above absolute zero. And all European countries are members of that since the 1950s. CERN was started in the 50s after the Second World War to bring physics back to Europe after it had been decimated by the fighting, and bring physicists from Germany, France, Italy, Britain, and so on, all together, working together as a force for peace in the world. And I've given talks about particle physics for peace because we collaborate globally. That's another picture of me in that tunnel. And this is actually me. I would put some detectors along the beam line there, so that's me in the LHC tunnel. And you see it goes off slightly curved, but going round. And these protons go around this 16-mile around tunnel, and the quarks inside can, anyway. And so there are 4 detectors at the Large Hadron Collider at places where the beams collide, and 2 big ones that found the Higgs. And this is Atlas. And look, you see the tiny people down there. Can you see the little people? Because it's a huge thing. It's an amazing huge thing underground. You can't see the whole thing because it's down in the cavern. Here's actually a picture of it, and you can see somebody standing down there. And those are toroidal coils for this magnet. The magnetic field goes around a toroid. And they co-discovered the Higgs boson with CMS. And you see that picture, and then my artist friend pointed out that it looks rather like this basilica, Temple de la Sagrada Familia in Barcelona. Okay. And the architect of that, called Antoni Gaudi, it's still being constructed, I think, in Barcelona. But a quote from him: nothing is invented, for it's written in nature first. Originality consists of returning to the origin. I think that's quite a nice sort of quote. And this is now the experiment that I've been working on, called CMS, compact muon solenoid. Compact doesn't mean small, it means just chock full of electronics, right? And you see the people down there. This is when it's in open state. When it's running, the sides close in and they match, so it's all sealed up around the collision point in the middle there. It's 12,500 tons of iron, 80,000 crystals of lead tungstate. Lead tungstate's clear, transparent material, but it's 98% metal and very dense. And that we use for detecting electrons and photons. It's got 700,000 channels of electronics. There are more now, actually. That was a few years ago. And every second when it's running, we write the information in 10,000 Encyclopedia Britannicas. And the information is sent over to the US and spread out to universities so we can analyze it over here. So coming back to this thing that Jim Verdi and I did in 1989, and he gave a talk about this, and you see they'd calculated what the Higgs signal might look like in 2 photons, depending on its mass. The top 2 plots are for a mass of 100 GeV Higgs, the bottom for 150 GeV Higgs. And you see the little blip down on the right. You can do it very, very challenging. But if we had a much better calorimeter, that blip could show up as a narrower spike. On the right, you see the discovery paper in 2012 and how we actually did discover it with the gamma-gamma decay mode as a little blip there on the distribution. And that required a more sophisticated analysis, but that was the discovery channel. And in our paper on the left, we said this might be a way to find it, but very hard, but we got there. And this is, on the left, you see a picture of one of the events producing 2 high-energy gamma rays, photons. They're shown as the green lines coming out there. And that could be a Higgs decay, or it could be just a background, that distribution, the background distribution you see. And on the right, you see a little blip there with a red line of, that's the Higgs to ZZ to 4 leptons, which was the other channel that we talked about. And then the discovery announcement on July the 4th, 2012, and that's at CERN, and there was a Fermi lab at 3 o'clock in the morning. We all gathered in the control room there to participate in it remotely, and there was a conference in Australia at the same time. And this is when it was announced by those two experiments, Atlas and CMS, both coming up with a signal that was significant enough that is very unlikely to be produced by chance, at the same mass, 125 GeV. And in front you see the director generals, and Higgs was there in the audience. He'd come down for it, and he was very emotional. He had tears in his eyes. I never thought it would happen in my lifetime, he said, because it was in '64 he proposed it, and finally in 2012 we got it. And it hit the headlines around the world, actually. Economist, Giant Leap for Science, and showed on Physics Letters cover that plot. And then on the left you see, the top is Joe Incandela. He was a spokesperson of our CMS experiment at the time. And in the middle you see Fabiola Gianotti. She was a spokesperson of Atlas at the time. Later she became CERN Director General, and she's just retired and handed over to an Englishman, actually, as new Director General. And at the bottom you see Rolf Hoyer, who was a CERN Director General at that time, announcing, "I think we've got it," he said, "I think we've got it." And that picture was the front page of the New York Times. Physicists find the elusive particle seen as a key to the universe. I think we have it. A cheer of the home research. We found it, we found the Higgs boson, a needle in a haystack, right? It really was a needle in a haystack. And woohoo, people are still sciencing. So a lot of publicity around this. It hit the headlines and popular culture. And you see here just front pages of many papers around the world that were just put up on a notice board at CERN. Then the Higgs boson walks into a church. The priest says, "We don't allow Higgs bosons in here." The Higgs boson says, "But how can you have Mass? Without me, how can you have Mass?" Okay, and here's another quote that I think are funny. Of course, you know about the guy on the left. "Christians are misunderstanding the God particle," he said. "In the beginning, the Higgs created the heavens and the earth. But I figured, who are people going to believe, God or some boson?" At the end of the Higgs announcement, one of the CERN team will pause, nonchalantly say, "Oh, one more thing," and then calmly teleport away. "Are you there, God particle? It's me, average person that doesn't understand you." On the news, in American news, "That's all the time we have for the God particle. Right now, let's meet your new hot dog eating champion." So, now, don't read this, but as the frontiers of knowledge expand, the frontiers of our ignorance expands. More and more questions arise. And these are a whole list of questions that we still have. We found the Higgs boson. There could be others like it with different masses. But we still have so many questions. Is this particle, does it have the properties we expect? Are there more than 3 dimensions of space? I won't go through them, but why are there 3 families of matter particles? Why do the forces unify and so on? What is dark matter? What is dark energy? What would happen in deep time? Is time infinite or finite? What happens to the antimatter? I think there will be questions or answers as long as we are here to ask them. So why is it called the God particle? Actually, there are 4 possible answers. You can choose one. A, it sells books. The publisher. So Leon Lederman he was a director of Fermilab. He wrote a book, and it got called the God particle. He said, "I wanted to call it that goddamn particle, but the publishers insisted on calling it the God particle. It certainly sells books." The field is everywhere throughout the universe and allows life to... That's one reasonable answer. This Higgs field fills the universe, and it's everywhere, and it allows life to exist. If that field was turned off, we wouldn't be here to talk about it. And the 4th answer is, because if I put God particle in this title of this talk, you might have come to the talk, otherwise you might not have come to the talk. But anyway, say God particle one more goddamn time. Thank you. Now time for questions. Right. I have to wait.
Mike, on various moments you mentioned that about the God particle and all, but I just wonder if there was cooperation involved, because this morning my wife and I worked out our Wordle puzzle in the New York Times. Worked out our Wordle puzzle in the New York Times and came up with the answer quark. So we're wondering if there was cooperation between you and the New York Times in this presentation.
Is this working? Oh, yeah, thank you. Okay, no. Quark. What's the word quark? I mean, Gell-Mann, who invented the idea of quarks, he was a polymath. He read so much. And quark comes in a book by James Joyce, Finnegan's Wake. And he used the word quark. Anyway, what was the question? New York Times. What about New York Times? I don't talk to New York Times. I haven't talked to them at all. But I mean, when CERN made that announcement, it had been searched for so long. It's a key to the standard model of particles. We have this so-called standard model. It's not really a deep theory in a way, because it doesn't explain so many things. All those 12 particles, the leptons and quarks, they've all got different masses. And that's come from some symmetry breaking, but we don't have a theory for exactly how that works. The theory says that particles coupled to the Higgs field proportional to their masses, and we've tested that and it seems to work fine. But that doesn't really explain why they've got the different masses in the first place. It's some symmetry breaking that could have been random, and personally I think that it happened that way in our universe, but there's gazillions of other universes it didn't happen that way with other particles and forces. But that's
I have a question.
Yeah.
You mentioned all of the European cooperation it took to create CERN. And
Yeah.
I don't know if you happen to have any knowledge about how much American contribution went into this back in the day when the U.S. was supporting scientific research.
Right. Yeah. So after the Second World War, when of course physicists were sort of heroes because they had the atom bomb and it stopped the war and so on. But science in Europe had been sort of decimated. Europeans, some had come to the States, worked on that, and then actually it was I.I. Rabi, an American, a Jewish American, who had said Europe should have a physics laboratory to sort of balance what we're doing in the United States. We shouldn't have it all in the US. We need a European laboratory, bringing European countries together. UNESCO was a port where they did that, a UNESCO, United States Education Site. And so he sowed the seed for having CERN. And so ever since CERN was developed, all member states, all countries in Europe became member states with one exception, which is Ireland, and they're now joining. Ireland. But then now we collaborate all over the world. In fact, I have I'll show you one. This is actually quite old, it's 2013, but you see there on the left all the list of member states. There's 6,831 people in the member states of CERN in the blue there. And then in green you have observers, like USA as an observer, and Russia, Soviet Union as an observer, as it was. And then on the right, in the red, you have others with numbers of physicists or engineers who work at CERN. There's nearly 1,000 of them. This is back in 2013. I haven't got an update on this, but it's global. You see, the only part of the world really not involved in CERN is Africa, or was Africa, apart from South Africa. And, some countries in Africa really, well, we want to get African physicists who do well at school to come to CERN for a year or two and then go back to Africa with the knowledge that they've gained and so on, to build science up in sub-Saharan Africa. So that's that. Oh, this is another technical diagram why protons are stable and neutrons are not. But anyway, that was. Okay, more questions. And by the way, this talk will be on YouTube, I think, and in a few days. So if you missed it, well, you didn't miss it, but your friends missed it, they can see it. Any more questions? I'm sorry I wasn't looking at you. You may have been raising your hand during the talk, but I tend not to have noticed them. So now you all know about the Higgs boson. And we physicists don't like to talk about the God particle, but when we're talking in public, it's okay. Oh, and by the way, so this book came out last year, Space, Time, Matter, 100 Short Stories About the Universe. 100 Short Stories About the Universe. And it's got 100 short non-fiction stories, and included in here you have articles about Mr. Higgs' boson, Professor Higgs particle. There's 18 science poems in the back, so you're welcome to buy a signed copy for $20. And I've just finished and submitted to a publisher another book, which is 60 years of experiments in particle physics, a sort of memoir with stories of my life in particle physics. So that may be published by a publisher, not Scientific American. It's called this year sometime. Anyway, there's the book. And thank you for your attention. And maybe go to the National Academy in a couple of weeks or so and see this exhibition that Shanti Chandrasekhar and I have put together. Let me know if you want to talk next month. We're looking for a speaker. Thank you.